People love Venn diagrams. One oval you get two regions, two ovals gives you four regions, three ovals gives you eight. So naturally four ovals should give you 16, right? Sorry, if you count really carefully, you'll see that there are only 14 regions. Two regions vanish. Where did they go? The geometry has failed us. But what are these regions really? Now, each of these regions is supposed to represent a set in Venn diagrams. 12 is a region that is supposed to be a combination of the sets A, B, C, D. Now, if you look at the region 12, it's inside A and it's inside B, but it's not inside C and it's inside D. Now, if two regions are missing, we can't represent all combinations of four sets faithfully. Let's test it out with real sets. Here are four subsets of the numbers from 0 to 15. Try to place them all exactly in a Venn diagram. And if you do that carefully, you should be able to see that certain numbers go missing. In my diagram, you see that 5 and 10 are missing. Now, why is it that 5 and 10 are missing? If you look at 5, you see that it's in B and D but not in A and C. And 10 is in A and C but not in B and D. But these overlaps just don't exist in the diagram. So therefore the circles just can't draw them. Now what about doodling Venn diagrams as blobs? Let's say we don't want to draw it as circles. Alright, so let's write all the numbers. We could use ovals for A and for C. But if we allow ourselves to draw non-oval diagrams, then we can indeed represent these four subsets faithfully as a Venn diagram. So non-oval shapes, blobs, do represent these four sets. So circles have failed. Why do they fail? But blobs seem to succeed for now. But can we really trust them? What does it even mean to reason with blobs? In this video, we will answer these questions and think deeply about Venn diagramming, which will lead us to uncover a hidden principle that stretches from set theory all the way to probability and topology. By the way, I'm Shrikant and welcome to AHA Problems. Today we're going to nitpick Venn diagrams until we uncover what they really mean. Now let's see why set theory is not the same as drawing oval-shaped diagrams. A single circle divides the plane into two regions, the inside and the outside. Add a second circle and it meets the first in at most 2 points. From the point of view of the new circle, these intersections split it into two arcs. Each of these arcs carve out a new region. The inner arc carves out region 3 from region 1 and the outer arc carves out region 4 from region 2. So we get totally 4 regions. We know that when we have 3 circles, we can have a maximum of 8 regions. Now, suppose you draw out a 4th circle. This 4th circle can meet the existing 3 circles at a maximum of 2 points each. So we can have a total of 6 points in maximum as intersection points. These 6 points divide the new circle into 6 arcs. And each of these arcs divide the intercepting region into another region. So therefore we get 6 new regions. So starting from 8 and adding 6 new regions, we see that we get a maximum of 14 regions. That means nobody in the world can draw 4 circles and get more than 14 regions. In fact, we can solve this problem in great generality. If Rn is the maximum number of regions obtained by drawing n circles, then we have the following recursion. By drawing the n plus 1 circle, it can intersect the earlier n circles in at most 2n points, and these 2n points will produce 2n new arcs, and each of these arcs will add a new region. Solving this recursion leads to the formula n squared minus n plus 2 is equal to Rn. Now, this formula is a bit tricky because for n equal to 1, 2, 3, you see a pattern of doubling the numbers which seem to hold until n equal to 4. Blob saved us this time. Circles have already betrayed us at 4 sets. What's to stop blobs from betraying us later? In math, it works is a dangerous attitude. We have to think deeply about the relationship between set theory and Venn diagrams. Set theory talks about sets, elements, subsets, and operations like union, intersection, and complement. If you think about Venn diagrams, what first comes to your mind? It'll be about drawing shapes, shading overlaps, staring at subparts. When we reason with them, we are pretending that these operations on sets and these drawings are essentially the same thing. We believe the algebra follows the geometry. Now let's try to actually retrace our thoughts when we reason with Venn diagrams. On the left, I will write set theory thoughts, and on the right, I will doodle Venn diagrams throughout our reasoning. Set theory always begins with a universal set. Everything we talk about lives inside here. Now, in the Venn diagram side, we just pull out a piece of paper and get started. The piece of paper is the plane that you see in front of you on the right. Now let's say the problem reads something like A and B are subsets of U. The moment we read that, what we do is we start drawing a couple of blobs. When we read that we want to look at A intersection B, we start shading the overlap of the two blobs. Now, if you think about this entire process carefully, already you see the issue. We are treating the blobs on the right as if they are the sets on the left. This is the pretense that we have built into every Venn diagram. Suppose the problem goes on and it lists the finite sets A and B, just a few numbers. We mark these points in our blobs. On the right, A and B are actually regions of the plane with infinitely many points. But we are pretending it is the set on the left, which has only finitely many points. So what's really happening here? Now here's the resolution to what is the art of Venn diagramming. And it comes from set theory itself. You see the pretending that we did, thinking of elements of the universal set as points in the plane? Now this is really a map, an assignment, where we are assigning every element of the universal set to points in the plane. Suppose we now look at a subset A of U. Immediately in the Venn diagram side, we draw a blob R, and we are going to pretend R is the same as U. But what does that mean? Let's try to understand what A is in terms of P and R. In fact, let us say what it is in English first. A is the collection of all elements of U that land in R under the map P. In fact, if you say it in set theory language, it is the set of all U belonging to U such that P of U is in R. In other words, it's all the elements of U that we pretend lie in R. This construction that we have done that relates R and A requires a name. In fact, what we have done is using P and R, we have constructed A. I will denote it by P sharp of R. Now here's a quick note. If you read any textbook, they will usually denote it as P power minus 1 of R. Now I don't like this notation personally because it's a little confusing. P power minus 1 already has meaning. Usually we reserve it to talk about the inverse of P. But the notion of P sharp of R exists even if P is not invertible. So to save that confusion of whether P is invertible or not, I use P sharp. With that note out of the way, let's understand what P sharp of R is. If you start with a region R and you apply P sharp, you land back in U. So P sharp is the tool that allows you to go from blobs to subsets of U. This P sharp of R has a name and is usually called the preimage of R under P. With this construction, we are finally ready to understand what Venn diagramming is. The art of Venn diagramming is taking a preimage of a region and pretending it is the region itself. Does this hold up? When we want to reason with Venn diagrams, does it work? So what do I mean by that? Usually, we don't just stop at identifying the set with its region. So if I have some diagram like this, now we know that we should not call the region the blob as A. Instead, we should give it a new name R, and the preimage of R is actually A. Similarly, the other region there should be S, and the preimage of S is really the set B. Now the overlap, which is written as R intersection S, you can again take the preimage of that. And usually when we reason with Venn diagrams, we say that preimage of R intersection S is A intersection B. In fact, a little more emphatically, we can write A intersection B as preimage of R intersection preimage of S. So the question we are really asking is, does the preimage construction preserve intersections? Remember, the preimage transports drawings into set theory. So the first question we are asking is whether preimage takes the overlap of R and S, and does it give you the intersection of the preimages? The next thing you can ask is, if you take two regions R and S and combine them, whether the preimage goes to the union of the preimages. And finally, we can ask, if you take everything outside a blob R, whether its preimage is the complement of the preimage. Now, if you look at it really carefully, I have phrased everything as preimage of a geometric operation is whether it is a set theoretic operation. In simple terms, we could write it as, does the preimage map respect the Boolean operations? This is the essence of Venn diagrams. In fact, we can draw blobs and reason with Venn diagrams if all these three operations work. And does it work? The answer is yes. So this becomes an exercise in set theory. In fact, it's a really simple exercise that I urge all of you to do, and prove the theorem that the preimage map respects Boolean operations. Topology is sometimes called the art of rubber sheet geometry. You can bend, twist, or stretch the sheet, but you can't tear it or glue it. And here's the amazing part. The whole idea is captured by preimages. To make sense of it, let's define an open set as just a collection of nearby points. A function is called continuous if the preimage of every open set is open. In other words, when you pull regions back through this function, that is apply the preimage, nearby points stay nearby. Think of stretching a rubber band. Points that are close after stretching came from points that were close before. That's continuity. But if you glue a cut band together, 2 points that look close after gluing actually came from far apart before. The preimage doesn't preserve open sets, so gluing is not continuous. And that's the punchline. The same preimage principle that makes Venn diagram work also gives us the modern definition of continuity, and it powers the whole field of topology. Now, let's switch to probability. Probability is the study of randomness. It discusses how to assign chance to events. Take the simplest possible experiment. Picking a real number at random between 0 and 1. Now, you can never specify a real number to all its decimal places. So realistically, we can only talk about ranges of values. That's why the basic events we care about are intervals. Think of a real experiment. Let's say measuring a height, weight, or a voltage or something like that. In fact, let's take height. Each measurement maps outcomes of the experiment to the numbers on a line. For example, here we are measuring the height of this girl. Now, here's the key. We already know how to assign probabilities to intervals. Pre-images let us pull back those intervals through the measurement, turning them into real-world events. That's what lets us say the chance that the height of this girl is between 2 and 3 units is the same as the probability of all outcomes that map into that interval. And this is the definition of a random variable, a function whose pre-image of every interval is an event. And in the end, that's what makes probability work. So let's recap. We began by puzzling over why circles failed to capture 4 sets. Then we asked if blobs could do better and discovered through pre-images they can. That same idea turned out to power topology and probability. But notice the real journey. We puzzled and we thought carefully. Finally, we spelled things out with precision. And once we posed the problem in its most natural form, the solution was automatic. And that, my dear viewer, is the true essence of doing mathematics.